A zircon crystal recovered from the Jack Hills of Western Australia measures roughly the width of a human hair. It is 4.4 billion years old, the oldest solid material yet found on Earth's surface, and under the right instrument it still carries temperature data from the oceans that formed around it. Not a metaphor. An actual number preserved in mineral lattice surviving plate collision and magma, and the slow grinding weight of deep time. Researchers did not go looking for a mystery when they found it. They were looking for a baseline. What the crystal gave them instead was a reminder. Some things survive the erasure. The question worth sitting with tonight is what else might have, and whether what we call our world might in some geologically quiet way be built on the ruins of something that came before. Tonight this episode follows a question that sounds simple on the surface but grows heavier the longer it is held. What if our world was built on the ruins of an older civilization, one so thoroughly absorbed by the planet that it no longer reads as artificial? Not a claim, a possibility worth tracing carefully in the same way a geologist traces a fault line, not to predict collapse, but to understand the shape of what has already happened. We will follow three traces through this question. The first moves through chemistry through isotopic ratios and sediment anomalies that some researchers argue may be harder to explain than they first appear. The second moves through biology, through the way living systems carry history forward in forms that no longer point back to their origin. The third moves through absence itself, through the specific silences in Earth's record that may mean nothing or may mean that something has already been folded so completely into the planet that we have stopped calling it evidence and started calling it baseline. None of these traces will resolve into a conclusion tonight. That is not what this space is for. What they will do is slow the question down until it is comfortable to hold in the dark without needing an answer before sleep arrives. It helps to begin with scale not as abstraction, but as weight. Earth has been reshaping itself for over 4 billion years. On that timeline, a civilization lasting 1 million years would occupy less than a single frame in a very long film. It would not leave a monument. It would not leave ruins in any sense we would recognize from the surface. What it might leave, if it left anything at all, would be something quieter, a slight tilt in a ratio, a distribution of elements that seems almost but not quite what the models predict. A planet that behaves as though it has been tuned without any tuner visible in the record. The word that keeps surfacing in the scientific literature around this question is Silurian. The Silurian hypothesis, named not for mythology but for a geological period, asks a technically precise question. Could an industrial civilization have existed in Earth's deep past without leaving traces we would currently recognize as artificial? The researchers who proposed it did not answer yes. They answered something more unsettling. It is harder to rule out than intuition suggests. The absence of obvious evidence, they noted, is not the same as evidence of absence, especially across timescales where the geological record itself contains gaps measured in tens of millions of years. That distinction deserves weight. It does not dissolve the question. It sharpens it. Earth is not a museum. It is an active system that grinds, melts, compresses and recycles its own surface continuously. Plate tectonics alone return ocean floor to the mantle on timescales of a few 100 million years. Entire chapters of planetary history are missing, not hidden, not suppressed, simply gone processed back into the system that produced them. We reconstruct what we can from what survives. What survives is selected by physics, not by importance. This matters because it changes the shape of the question. We tend to ask, where are the ruins? But ruins belong to civilizations that built in ways that resist nature, that used materials nature takes centuries to dismantle, that left sharp edges against the background. A civilization that reached a different relationship with its environment, one organized around integration rather than extraction, would not produce ruins in any conventional sense. Its most advanced phase might look from the outside like a planet functioning normally. The trace would not be a structure. It would be a condition, a slightly altered baseline that later inhabitants would take for granted, the way a person moving into an old house takes for granted which floorboards carry weight and which do not. That possibility is what the three traces tonight are designed to approach, not to confirm but to feel the outline of. Each one follows a different angle into the same question. If something acted here before us long enough ago, that even its chemistry has blurred into the background. What would we be looking for, and would we recognize it? The planet beneath you is old in a way that resists imagination. Whatever its full history holds, it has continued forward without pause, absorbing, recycling, resetting. Our presence is one interval within that motion. So we follow the first trace, and we begin with what the chemistry of ancient sediment does and does not preserve. What deep time does to evidence? 66 million years ago, an asteroid roughly 12 kilometers wide struck what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to billions of nuclear warheads simultaneously excavated a crater nearly 180 kilometers across and threw enough debris into the upper atmosphere to darken skies globally for years. It ended the reign of non-avian dinosaurs which had dominated terrestrial life for over 150 million years. And yet the crater itself was not formally identified until 1978. It took the development of subsurface geological mapping, the careful analysis of gravity anomalies, and decades of drilling into sediment beneath the Gulf of Mexico before the outline of that impact became legible to the people looking for it. The most consequential single event in the last 100 million years of Earth's history left a mark so thoroughly buried, so completely absorbed into subsequent geology that it went unrecognized until the late 20th century. This is not a story about incompetence or oversight. It is a story about what time does to evidence, even evidence of catastrophic scale, even evidence that reshaped the entire trajectory of life on this planet. If an asteroid impact of that magnitude can hide in plain sight for tens of millions of years, the question of what else might be hidden, not by design, not by conspiracy, but simply by the patient operation of geological process, becomes less exotic than it might first appear. Tonight's question does not require catastrophe. It does not require a war, a cataclysm, or a single dramatic extinction event. It only requires the possibility that something existed here before us, something complex enough to qualify as a civilization, and that it ended or changed or dissolved quietly enough that the planet absorbed it the way it absorbs everything else, through pressure, through heat, through the slow recursion of water over stone across intervals of time, too large to hold in ordinary imagination. To hold this question seriously, it is necessary to sit with the actual dimensions of the problem rather than the intuitive ones. Earth is approximately 4.5 billion years old. Life in some form has been present for perhaps 3.7 billion of those years. Complex multicellular life, the kind that builds structures visible to other complex creatures, has existed for roughly 600 million years. Within that window, humans in their anatomically modern form have been present for perhaps 300,000 years. Technological civilization, the kind capable of altering atmospheric chemistry and extracting metals from deep geological formations at scale, has existed for less than 300 years in any meaningful sense. On a timeline compressed to a single calendar year, the entirety of human history from first stone tool to the present occupies the final 11 seconds of December 31st. The discomfort in that number is not philosophical. It is technical. It changes what no evidence actually means. If technological civilization can rise and fall in what amounts to a geological instant, and if the geological record routinely fails to preserve even obvious physical evidence across spans of tens of millions of years, then the question of whether a prior civilization could exist without leaving recognizable trace is not fringe. It is almost a structural expectation of how planetary recording works. What would remain, not cities. Cities even built from stone depend on maintenance, and without it they are reclaimed within centuries by vegetation, by water infiltration, by the disaggregation of mortar and the slow colonization of root systems. Metal corrodes, plastics fragment under ultraviolet radiation and microbial pressure over decades, then disperse into particle sizes that blend into sediment chemistry without announcement. Nuclear waste, arguably the most durable product of industrial civilization, would leave a detectable isotopic signature for perhaps a few million years before becoming ambiguous against natural background variation. After 50 million years, the physical artifacts of human civilization would be largely unrecognizable as artificial. After 500 million, they would be for all practical purposes invisible. This is not speculation about distant futures. It is the ordinary operation of the geological system applied backward in time with the same logic it applies forward. What survives in the deep record are not objects but ratios, not structures but distributions. The geological record does not preserve the shape of things. It preserves the chemistry of conditions, the residue of processes, the numerical fingerprint of events that altered the balance of elements in ways that subsequent layers of rock and sediment happened to lock in before further change could erase them. And this is where the first trace of tonight's question begins to take form, not in anything tangible, not in an artifact you could hold under a light, but in the subtle deviation of a number from what a purely natural model would predict. Some researchers have noted that certain transitions in Earth's sedimentary chemistry, particularly in isotopic ratios of carbon-oxygen, and specific trace elements occur within geological layers that correspond to periods of otherwise unremarkable stability. No mass extinction marker at the boundary, no clear volcanic signature, no detectable layer of asteroid debris, just a quiet shift in the ratios persisting across a span of a few million years before the numbers return to something more consistent with background geological variation. Most of these anomalies carry proposed natural explanations, and most of them are almost certainly correctly explained by those natural processes. But the residue of the unexplained, even when statistically small, has a way of sitting in the back of careful thinking without fully dissolving. The Silurian hypothesis, proposed in peer-reviewed literature in 2018, by researchers Adam Frank and Gavin Schmidt, asked precisely this kind of question. Not whether a prior civilization definitely existed, but whether if one had the geological record as currently understood would be capable of preserving its signature in any form we could distinguish from natural variation. Their conclusion was cautious and significant in equal measure. Some signatures might persist, particularly in organic carbon isotope profiles and certain trace element distributions, but many would not survive the timescales involved, and the ones that might persist would be, in their own phrasing, difficult to separate from background noise without knowing in advance what pattern to search for. That circularity is the technical heart of the problem. You cannot search effectively for something you have not yet defined, and you cannot define it without at least one confirmed prior example to calibrate against. Earth, as far as the current record indicates, provides no confirmed example. What it provides instead is the set of conditions under which a prior civilization's traces would be nearly indistinguishable from the ordinary chemistry of a planet doing what planets do, which is not the same as proving those traces are absent. The geological record holds Earth's history in layers, and each layer is read by instruments and methods designed to find natural causes. That is entirely appropriate. Natural causes are almost always sufficient, and the history of science is full of anomalies that dissolved into elegant natural explanations once the right question was asked, but almost always preserves a margin, and it is in that margin, not in sensationalism, not in the suspension of critical thinking, but in the honest residue of what the record cannot fully account for, that tonight's first trace is found. We follow it now into what the chemistry of ancient sediment preserves after the structures themselves are gone, the language of sediment. Carbon has a memory, not in any metaphorical sense, but in a precise isotopic one. The ratio of carbon-12 to carbon-13 in a sedimentary layer carries information about the biological and chemical conditions that prevailed when that layer was deposited, and that ratio, once locked into carbonate rock or organic rich shale, tends to remain stable across extraordinary spans of time. Geochemists use this stability as a reading instrument, a way of reconstructing ancient ocean temperatures, atmospheric compositions, and the relative intensity of biological productivity in seas that no longer exist. The method works because the signal is consistent enough to be meaningful and sensitive enough to register disruption. What it occasionally registers in certain layers is a disruption that does not match cleanly with the event surrounding it. The terminology for these events is carbon isotope excursions, and they appear throughout the geological record at moments of known crisis: the end, Permian extinction, the Paleocene-Eocene, thermal maximum, the Cretaceous-Paleogene boundary. At those moments, the isotopic signal shifts sharply, and researchers can correlate the shift with independent evidence of volcanic activity, bolide impact, or rapid biological collapse. The method is well established. The correlations are robust, and the scientific community has reasonable confidence in the interpretive framework. But there are smaller excursions, quieter ones, not associated with any confirmed extinction event, not correlated with known volcanic provinces appearing in layers that otherwise look unremarkable where the explanation remains genuinely provisional. These are not anomalies that scientists regard as embarrassing or suppressed. They are simply unresolved, sitting in the literature as open questions awaiting better data or more precise dating. The patience required to hold them as open questions rather than forcing them into existing explanatory categories is where the more interesting thinking begins. What would a prior industrial civilization's chemical signature actually look like in the sedimentary record, assuming enough time had passed to blur its sharpest features? This is the question that Frank and Schmidt attempted to model in their 2018 analysis. And their findings are worth dwelling on carefully. They noted that modern industrial activity has produced a measurable shift in atmospheric carbon isotope ratios, specifically a depletion of carbon, 13 relative to carbon-12 caused by the burning of fossil fuels, which are themselves depleted in carbon-13, because they derive from ancient biological material. This shift, called the Suez effect, is already detectable in ice cores and sediment records from the last century. In a geological layer deposited 10 million years from now, it might appear as a brief but distinctive excursion in the carbon isotope profile, a pulse lasting in geological terms almost no time at all, but chemically identifiable if the right instruments were applied to the right layer. The duration of the signal they noted would depend on the duration and intensity of the industrial activity. A civilization that industrialized briefly and then collapsed, or transitioned to cleaner energy systems before disappearing, might leave a narrower and fainter pulse than our own projected signature, potentially narrow enough for them to be difficult to distinguish from natural variation at the resolution currently available for ancient sediment analysis. This is the crux of what makes the isotopic trace simultaneously compelling and frustrating. The very conditions that would make a prior civilization's signature faint are also the conditions we would associate with a civilization that had in some sense succeeded, one that recognized the limits of high emission activity and adapted before those limits became catastrophic. A civilization that burned through its resources rapidly and then collapsed might leave a cleaner isotopic record of its own disruption. A civilization that moderated its impact, integrated into planetary cycles, and faded gradually might leave almost nothing. The irony embedded in that asymmetry deserves a moment of quiet attention. The civilizations most likely to survive long enough to disappear gracefully are also the civilizations least likely to leave a recoverable signature. Beyond carbon, there are other isotopic systems that carry long-duration memory. Lead isotope ratios in sediment and ice reflect the history of a metal smelting with surprising sensitivity. Lead isotopes fractionate distinctively during high-temperature metallurgical processes, and even relatively ancient human smelting activity from the Roman period has left detectable lead anomalies in Greenland ice cores and alpine lake sediments that persist cleanly in the record 2,000 years later. Extrapolating that sensitivity backward raises a question that is difficult to dismiss without careful thought. If Roman-era metallurgy left a 2,000-year-old isotopic fingerprint visible in Arctic ice, what would a more extensive industrial period leave in sediment deposited 50 million years ago? And would that fingerprint, diluted by digenesis and compressed by subsequent burial, remain above the detection threshold of the methods we currently use to analyze ancient rock? The answer based on current geochemical modeling is that it might not. Not because the signal was never there, but because the processes of sediment compaction, mineral recrystallization, and thermal alteration that accompany burial, over tens of millions of years, progressively degrade the precision of isotopic records in ways that are difficult to fully correct for. There is a lake in northern Canada called Crawford Lake in Ontario that has become significant in a different but related context. Its unusual stratified structure, a meromictic lake in which the deep waters do not mix with surface waters, has preserved an extraordinarily detailed annual sediment record extending back several thousand years. The layers are so precise that individual years can be distinguished, and within those layers, the arrival of European settlement is visible as a clear chemical discontinuity, a shift in pollen types, an increase in certain heavy metals, and a measurable change in carbon profiles, all concentrated within identifiable annual deposits. Crawford Lake was designated in 2023 as one of the candidate sites for the formal definition of the Anthropocene boundary, the proposed geological epoch marking humanity's transformation of planetary systems precisely because its record preserves human chemical influence with a resolution rare in natural archives. The relevance to tonight's question is not the Anthropocene itself, but what Crawford Lake demonstrates about the relationship between the intensity of a record's preservation and the fragility of that preservation over time. A lake that stratifies cleanly and accumulates undisturbed sediment for 3,000 years is already exceptional. A lake that does so for 3 million would be essentially impossible. The conditions required for high-resolution chemical preservation are rare, localized, and temporary. Scale the timeline further, and the chances of finding any such archive from a civilization operating hundreds of millions of years ago approach something very close to zero, not because the civilization left nothing but because the recording medium is not built to last. What the sediment record offers, then, is not a window but a filter one that allows certain kinds of signals through, while attenuating others, and that operates according to physical and chemical rules rather than any interest in preserving what once mattered to the creatures who lived through it. The filter is honest in its way. It does not hide things deliberately. It simply does not distinguish between what was significant and what was not, processing both with equal indifference across the depth of time. That indifference is what makes the second trace the one that moves not through rock chemistry, but through living systems worth following with particular care. What living systems remember? Consider what the mitochondria in your cells actually are. They are not structures that evolved within animal cells gradually through the slow accumulation of mutations and selective pressure acting on a single lineage. They are, according to the endosymbiotic theory now accepted as foundational in cellular biology, the descendants of free-living bacteria that were absorbed by a larger ancestral cell somewhere between 1.5 and 2 billion years ago, not digested, not destroyed, but incorporated. Their membranes preserved their metabolic function, redirected their genetic material, partially transferred to the host cell's nucleus, while a remnant genome remained inside the organelle itself. Every breath you draw depends on a merger that happened before complex life existed on this planet, and the organism that made that merger left no fossil, no artifact, no surface feature visible to any instrument. It left only its descendants embedded so thoroughly in the architecture of eukaryotic life that the boundary between host and absorbed organism became over 2 billion years effectively invisible. Biology remembered something that geology could never have preserved. This is the property of living systems that makes the second trace worth following with a different kind of attention than isotopic chemistry demands. Rock records events as chemistry, life records events as structure, as the arrangement of genetic sequences, as the topology of metabolic pathways, as the distribution of species across ecosystems, and as the specific forms of cellular machinery that solve particular problems in particular ways. These biological records are not permanent. They too are subject to erasure, to drift to the deletion of sequences no longer under selection pressure, but they operate on timescales and through mechanisms that differ fundamentally from the geological ones, and they occasionally preserve signals that sediment cannot. The question applied to the possibility of a prior civilization is not whether ancient DNA could survive hundreds of millions of years. It could not in any recoverable form. The question is more subtle whether a civilization that interacted with living systems at sufficient depth and duration might leave traces in the structure of those systems and the distribution of organisms, the architecture of ecosystems, the specific evolutionary solutions that appear across lineages in patterns that look under careful scrutiny slightly more deliberate than pure contingency would predict. Convergent evolution is the biological phenomenon most relevant here, and it deserves to be held with some precision. When eyes evolved independently in vertebrates, mollusks, and arthropods using different developmental pathways, different structural materials, different optical geometries, the conventional explanation is that the physics of light and the advantages of directional photosensitivity created strong selective pressure towards similar solutions across unrelated lineages. This explanation is sound. It's also, in its deeper implication, somewhat remarkable. It means that complex biological structures can arise independently through entirely separate evolutionary histories as well, arriving at functionally similar endpoints because the environment rewards certain solutions consistently. Intelligence, the capacity for flexible problem solving, for modeling the environment and acting on that model, shows the same pattern of convergence. It has appeared in varying degrees in primates, cetaceans, corvids, and cephalopods, each through independent evolutionary trajectories, each shaped by different neural architectures. The conventional reading of this convergence is that complex environments reliably select for cognitive flexibility. That reading is almost certainly correct. It also implies something that the question of a prior civilization makes slightly more uncomfortable if intelligence converges. Because the environment rewards it, then intelligence is not a singular accident. It is a recurring solution to a recurring problem, and recurring solutions have a way of appearing more than once on a planet with a 4 billion year head start. The biological trace does not depend on convergent intelligence alone. It extends into the specific ways that organisms modify their environments, and there's way those modifications persist long after the organisms themselves are gone. Ecosystem engineers organisms that alter physical or chemical conditions in ways that create habitat for other species, leave legacies that can persist for geological timescales in principle, even if the engineers vanish. Beavers are the standard human-scale example, but the pattern operates at every level of biological organization. Reef building. Corals alter carbonate chemistry across thousands of square kilometers. Mycorrhizal fungal networks restructure soil chemistry and plant community composition across timescales of centuries. Nitrogen-fixing bacteria altered the chemistry of Earth's ancient soils so thoroughly that their influence is still visible in the isotopic profiles of Precambrian sediment. A civilization that interacted with ecosystems primarily through biological means that managed landscapes through ecological manipulation rather than mechanical extraction that altered species distributions and nutrient cycles through sustained and intentional intervention might leave the kind of trace that looks millions of years later like a slightly unusual distribution of species, a slightly accelerated trajectory of ecosystem complexity, a slightly unexpected convergence of biological solutions in regions that have no obvious physical reason to share them. None of this is detectable in any specific current dataset. The point is not to claim a signal has been found in the biological record, but to note that the biological record, like the isotopic one, contains gaps and patterns that are interpreted through frameworks assuming a single lineage of intelligence on this planet. Those frameworks are appropriate given the evidence available, but frameworks are not facts. They are the instruments through which facts are read, and instruments have resolution limits. The biological trace of a prior civilization, if it existed, would not appear as a labelled artifact within a genome or a species distribution map. It would appear as a set of patterns slightly more ordered than chance predicts, and the distance between slightly more ordered than chance and consistent with natural selection acting on a complex environment is not always easy to measure with confidence. What remains, after the biology fades, is the third trace, the one built not from what is present in the record, but from the specific geometry of what is missing. The shape of what is missing. Absence is a difficult kind of evidence to work with, not because it is inherently less reliable than presence, but because it requires a prior expectation, a model of what should be there, before the gap becomes legible as a gap, rather than simply as the normal condition of things. A fossil record that contains no trace of a particular organism does not on its own tell you whether that organism never existed or simply never fossilized. A geological layer that shows no isotopic anomaly does not tell you whether nothing unusual occurred, or whether the signal has been smoothed away by the ordinary operations of diagenesis and mineral recrystallization over sufficient time. Absence speaks only in relation to expectation, and expectation is shaped by the frameworks we bring to the data frameworks that, in the case of Earth's deep past, are built almost entirely on the assumption that intelligence appeared here once recently and left no predecessors worth accounting for in the models. The resource distribution of Earth's crust is one place where this problem of expectation becomes particularly interesting to sit with. Certain metals and mineral deposits are concentrated in ways that geologists can largely explain through known processes: hydrothermal circulation, magmatic differentiation, sedimentary concentration, and the specific chemical conditions of ancient ocean basins. The explanations are robust and well tested. But the distribution of accessible surface and near-surface deposits, the ones that would have been easiest to reach and most attractive to any civilization dependent on metallurgy, carries a subtler question embedded within it. We tend to assume that the concentrations we find today are essentially what was always there minus what we ourselves have extracted over the last few centuries. That assumption is reasonable given a framework in which human civilization is the first technological presence on this planet. It becomes slightly less obvious once that framework is loosened even tentatively. If a prior civilization extracted certain near-surface metal concentrations over a sustained period, the remaining deposits might appear simply as the natural baseline diffuse lower grade requiring deeper extraction, without any obvious marker indicating that a higher grade surface deposit once existed and was consumed. The depletion would look like geology. It would be indistinguishable from what forms naturally in a world where no one came before. The rare earth elements offer a specific lens through which this problem can be viewed with some precision. Rare earths, the group of 17 metallic elements that includes neodymium, europium, and dysprosium, are not actually rare in terms of their abundance in the Earth's crust, but they are rarely found in the concentrated, easily extractable deposits that make mining economically viable. Their distribution is uneven in ways that geologists attribute to specific igneous and sedimentary processes that concentrate them selectively. Modern technology depends on them. Heavily electric motors, wind turbines, semiconductor components, and precision optics all require rare earth elements in quantities that current known deposits strain to supply. The question that the third trace invites not as an accusation but as an open examination is whether the relative scarcity of economically accessible rare earth deposits is entirely a function of natural geological process, or whether it carries within it any signature of prior extraction too old and too diffuse to distinguish from background variation. The current answer is that no such signature has been identified. The more careful answer is that no one has looked for it systematically using frameworks that would allow the question to be asked, because the question itself sits outside the standard assumptions of the field. There is a precedent in human history for this kind of invisible depletion operating at a much smaller timescale. The forests of the Mediterranean basin were extensively logged throughout antiquity for shipbuilding, for fuel, for agricultural clearance to a degree that transformed the ecological character of entire regions. By the time systematic ecological observation began in the modern period, the degraded scrubland and eroded hillsides of Greece, Lebanon, and North Africa were being described as the natural condition of those landscapes, their carrying capacity assessed against a baseline that was itself the product of the millennia of extraction. The cedars of Lebanon, famous in ancient texts as forests so dense they block the midday sun, exist today as a handful of protected remnant groves. A traveller encountering those hillsides without historical knowledge would have no reason to assume they were anything other than naturally sparse. The depletion had become the landscape scale-out process to geological time and planetary geography, and the principle extends uncomfortably far. What the third trace is pointing toward is not a specific missing deposit or a specific identified gap in any particular element's distribution. It is pointing toward the epistemological structure of the problem that we assess Earth's natural resource baseline using frameworks calibrated to a planet with one industrial civilization, and that if we are wrong about that assumption, we have no obvious way of knowing it from the inside, because the wrong assumption and the right one produce landscapes that look identical to each other across the timescales we can currently examine. The detail that refuses to go away is not dramatic, it is structural. The absence of evidence for prior depletion is not in itself evidence that prior depletion did not occur, it is evidence that prior depletion, if it occurred, succeeded in becoming indistinguishable from natural scarcity. That indistinguishability is not a clue pointing toward a conclusion. It is a reminder that the question has a shape. The current instruments were not designed to resolve. And it is in that unresolved shape, that careful, quiet margin, where the natural and the possibly not natural overlap without separation, that the fourth trace waits. The atmosphere that should not have lasted. For the last 540 million years, the span of time encompassing virtually all of complex animal life on this planet, atmospheric oxygen levels have remained within a range of roughly 15 to 35%. The lower boundary of that range sits just above the threshold at which sustained combustion becomes possible. The upper boundary sits just below the threshold at which organic material becomes so flammable that terrestrial ecosystems could not maintain their structure. Life as it currently exists on Earth, from the metabolic requirements of deep-sea invertebrates to the cognitive demands of large-brained mammals, is calibrated to function within this band. Drift significantly below it, and oxygen-dependent metabolism becomes unsustainable for complex organisms. drift significantly above it, and the biosphere faces a different kind of crisis. Forests ignite. At the touch of lightning, fire becomes a planetary scale force rather than a localized ecological one, and the carbon cycling that stabilizes long-term climate is disrupted at its foundation. The band is narrow, and for 500 million years Earth has stayed inside it. This is not on its own evidence of anything unusual. The scientific literature contains well-developed models, the GeoCarb series, the COPS model, and their various refinements that account for this long-term stability through a combination of biological and geochemical feedbacks operating without any central coordination. When oxygen levels rise, plant material becomes more flammable, fire increases, carbon is oxidized and returned to the atmosphere as carbon dioxide photosynthesis eventually draws that carbon back down and oxygen production moderates. When oxygen levels fall, fire decreases. Organic carbon accumulates in sediment. Its burial removes carbon from the cycle, and the balance shifts again. The system regulates itself through the interlocking operation of biology, geology, and atmospheric chemistry, none of which requires any awareness of the whole. The models are robust, the mechanisms are real, and yet applied with sufficient precision to the actual geological record the models produce. Oxygen curves that oscillate more widely than the fossil record's evidence of ecosystem continuity seems to permit. Which means that either the models are missing a stabilizing factor, or the fossil record is not capturing the full range of ecological disruption that actually occurred, or both. What stabilizes a planetary atmosphere over timescales longer than any individual feedback loop can account for is a question that the atmospheric sciences have not fully resolved. The Gaia hypothesis, proposed by James Lovelock in the 1970s and developed with microbiologist Lynn Margulis, suggested that Earth's biosphere functions as a self-regulating system, not through conscious intent, but through the aggregate effect of billions of organisms, each pursuing their own metabolic interests, the sum of which produces conditions favourable to the persistence of life itself. The hypothesis has been refined considerably since its initial formulation, stripped of teleological implication and reframed in terms of cybernetic feedback and systems ecology, and in its more rigorous modern forms it captures something real about how planetary biogeochemical cycles maintain stability. But it also leaves an open question at its edge. The feedback systems that Lovelock and Margulis identified operate within timescales of thousands to millions of years, and the stability they produce is approximate, not absolute. The geological record shows periods when those feedbacks were overwhelmed, when atmospheric oxygen crashed during the end, Permian extinction, when carbon dioxide spiked during massive volcanic episodes, when methane from microbial sources briefly dominated atmospheric chemistry in the deep Precambrian. Against that history of instability, the relative equanimity of the last 500 million years looks on careful examination slightly more stable than the models alone comfortably predict. One framework for thinking about this, not as proof but as a structural way of holding the question, involves what systems engineers call a set point. A regulated system does not merely fluctuate randomly within some range. It fluctuates around a central value returning to it when disturbed, because something in the system's architecture preferentially restores that value over others. Thermostats have set points. Biological organisms have set points for temperature, blood chemistry, and osmotic pressure. The existence of a set point implies that the system contains feedback mechanisms specifically tuned to that value, mechanisms that resist deviation more strongly as the deviation increases. What the atmospheric record of the last 540 million years resembles in its broad structure is a system with a set point not perfectly maintained, not immune to perturbation, but returning after each disruption to a range compatible with complex life in ways that pure physical chemistry and biological evolution do not entirely account for without additional stabilizing factors not yet fully specified in the models. The additional stabilizing factor most commonly proposed is the continental weathering feedback, the process by which silicate rocks exposed by tectonic uplift react with atmospheric carbon dioxide, drawing it down on million-year timescales and thereby moderating the greenhouse effect. This mechanism is real and important. It is also in isolation too slow to account for the regulation of atmospheric oxygen at the timescales relevant to the fossil record's evidence of ecological continuity. Something else, or several something else, must be operating at intermediate timescales, and the identity of those mechanisms is still an active area of research. Among the candidates being investigated are ecosystem-level feedbacks involving soil microbial communities, oceanic productivity cycles tied to dust-borne nutrient delivery and climate vegetation, interactions that modulate albedo and evapotranspiration in ways not fully captured by current Earth system models. Each of these is a legitimate and well-studied mechanism. Taken together, they narrow the gap between model prediction and observed stability without closing it entirely. The atmospheric trace is the most diffuse of the four followed tonight, and in some ways the most structurally important. It does not point to a specific anomaly in a specific layer. It points to a systemic property, the unusual long-term compatibility of Earth's atmospheric composition with the persistence of complex life, and asks whether that property is entirely the product of unguided feedback processes, or whether it carries folded into its history the influence of something that learned to work with those feedback systems rather than against them. The question cannot be answered with current data. What it can do is sit alongside the isotopic trace, the biological trace and the resource trace, as a fourth angle of approach to the same underlying shape, the outline of a planet that behaves in certain subtle ways as though it has been here before. The most direct challenge to all four of these traces comes not from a competing discovery, but from a competing framework, and that challenge deserves to be held with the same care as the traces themselves. The weight of the simpler explanation. There is a principle in scientific reasoning that does not get invoked often enough in conversations about deep time and anomalous patterns, not because scientists are unaware of it, but because it is genuinely difficult to apply cleanly when the subject matter is as complex and incompletely sampled as Earth's geological history. The principle is parsimony when two explanations account equally well for the available evidence. The simpler one is provisionally preferred, not because simplicity is a metaphysical virtue, but because simpler explanations make fewer assumptions, and fewer assumptions means fewer places for the reasoning to go wrong in ways that cannot be tested. Applied to the four traces followed across the previous chapters, parsimony asks a direct and uncomfortable question: do the isotopic anomalies, the biological patterns, the resource distributions, and the atmospheric stability actually require a prior civilization to explain them, or do they require only that the natural processes already documented in the scientific literature be allowed to operate in combinations and at magnitudes that current models have not yet fully characterized? The honest answer, held without defensiveness, is that they do not require a prior civilization. They require only complexity, the ordinary well-attested complexity of a planetary system with 4 billion years of interacting geology, chemistry, and biology behind it. This is the first and most important skeptical point, and it deserves to be stated with full force, rather than softened into a token concession. The carbon isotope excursions that appear in the geological record without obvious volcanic or impact correlates or anomalies within a framework that is itself incomplete. Earth's volcanic history is not fully mapped. The precise timing and magnitude of ancient oceanic anoxic events is still being refined. The sensitivity of the carbon cycle to changes in ocean circulation, in the distribution of continental landmasses, and in the composition of microbial communities in deep-sea sediments is imperfectly understood. When an anomaly appears in the isotopic record and resists easy explanation, the working assumption of the field, an assumption supported by the consistent success of natural explanations in resolving previous anomalies, is that a natural explanation exists and has not yet been found. Not that the category of natural explanations has been exhausted. That working assumption has been vindicated repeatedly across the history of geochemistry, and there is no principled reason based on the current evidence to abandon it in favour of a hypothesis that introduces an entirely new category of cause without direct supporting evidence for that category's existence. The second skeptical point concerns the specific architecture of the argument being made across the traces. Each trace examined individually relies on an absence or an ambiguity, an anomaly that natural processes do not fully account for, a pattern that looks slightly more ordered than chance predicts a stability that the models underpredict. But arguments built from absences and ambiguities are structurally fragile. In a specific way, they derive their apparent force from the incompleteness of the natural explanation, and the incompleteness of a natural explanation is not fixed. It changes as the science develops. The history of science contains many cases in which a genuine anomaly, one that genuinely resisted natural explanation for decades, was eventually resolved not by introducing a new category of cause, but by refining the understanding of known processes. The anomalous perihelion precession of Mercury resisted Newtonian explanation for 60 years before general relativity dissolved it. The origin of the lunar craters was attributed by serious researchers to volcanic activity well into the 20th century before the impact hypothesis became dominant. The argument that a pattern is harder to explain than it first appears is a description of the current state of knowledge, not a permanent feature of the phenomenon. Treating the current explanatory gap as evidence for a specific alternative explanation in this case, a prior technological civilization moves faster than the evidence warrants. The third skeptical point is perhaps the most fundamental, and it concerns the human tendency to read significance into patterns that arise from processes indifferent to significance. Pareidolia. The perception of meaningful form in random or semi-random input is not limited to seeing faces in clouds. It extends to the interpretation of data, to the construction of narratives from fragmentary evidence, and to the identification of anomalies as clues rather than as ordinary features of a noisy and incompletely sampled record. The 4 traces followed tonight are real observations in the sense that the underlying data is real. Carbon, isotope excursions do occur, convergent evolution is genuine, resource distributions are uneven, and atmospheric stability over deep time is imperfectly modelled. But the interpretation of those real observations as a coherent pattern pointing toward a prior civilization involves a series of inferential steps, each of which introduces uncertainty, and the compounding of those uncertainties across 4 separate traces does not produce a stronger argument. It produces an argument with 4 times as many places where the reasoning could be wrong. The pattern feels coherent because the human mind is exceptionally good at constructing coherent narratives from fragmentary inputs. That coherence is a property of the mind doing the interpretation, not necessarily of the phenomenon being interpreted. These 3 points, the sufficiency of natural complexity, the impermanence of explanatory gaps, and the unreliability of pattern perception under uncertainty, are not decorative concessions. They are the structural core of why the scientific community does not, as a working matter, treat the possibility of a prior terrestrial civilization as a live hypothesis requiring active investigation. The evidentiary bar for a claim of that magnitude is high, appropriately so, and the traces followed tonight do not clear it. Some researchers argue that the bar itself may need rethinking, that the specific character of the evidence a prior civilization would leave is sufficiently different from the evidence the scientific community is currently equipped to recognize that the absence of recognized evidence cannot function as strong disconfirmation. That argument deserves weight. It does not dissolve the skeptical position. It simply locates the disagreement more precisely not in the data, but in what counts as a meaningful signal against the background of a 4 billion year planetary record that no current framework fully describes. It may be natural. It may be chance compounded by the ordinary incompleteness of science at its edges. The discomfort that remains quite structural, refusing to fully dissolve even after the skeptical points are held with full seriousness, is that the pattern across the 4 traces retains its shape even when each individual trace is granted its most conservative interpretation. And a pattern that survives its own most careful scrutiny is not proof of anything, but it is not nothing either. The question that follows from that observation is not whether the civilization existed. It is what kind of civilization, if it did exist, would have been capable of leaving a world behind in the condition we find it, and what that capability would have required of the beings who possessed it. The civilization that learned to disappear. What would it actually require, not metaphorically but operationally, to leave a planet in the condition we find Earth with its atmospheric stability, its improbably intact biosphere, its long history of complex ecosystem recovery after each disruption, and its surface bearing no unambiguous signature of prior technological intervention? The question is not asking what a civilization would need to avoid doing. It is asking what a civilization would need to understand at a deep and sustained level in order to make integration rather than extraction the organizing principle of its entire relationship with the planetary system. That distinction between avoiding harm as a constraint and integration as a design principle turns out to matter enormously when thinking about what traces such a civilization would and would not leave behind, and why the absence of obvious traces might in a specific kind of civilization be the closest thing to a signature it could produce. Begin with energy, because energy use is the most basic expression of a civilization's relationship with its environment, and the one most likely to leave detectable chemical residue in the geological record. Human industrial civilization is characterized by the rapid extraction and combustion of stored chemical energy, fossil fuels accumulated over hundreds of millions of years of biological productivity at rates that outpace the planet's capacity to reabsorb the resulting byproducts. The signature of this process is already visible in the geological record of the last century, the carbon isotope shift, known as the Suez effect, the global spike in particulate black carbon in lake sediments, the measurable increase in atmospheric methane and nitrous oxide detectable in ice core records from Greenland and Antarctica. These are the signatures of a civilization in what might be called its extractive phase, the phase in which capability has outrun integration, in which the rate of energy use exceeds the rate at which planetary feedback systems can process the consequences. A civilization that passed through this phase and survived would do so only by developing energy systems that draw from flows rather than stocks from the continuous flux of solar radiation thermal gradients and chemical cycling that the planet sustains without net depletion, rather than from the concentrated stores that accumulated over geological time. Such a civilization's energy signature in the sedimentary record would be at its most advanced, nearly indistinguishable from the background energy processing of a biologically active planet. The distinction between flow-based and stock-based energy economies is not hypothetical in the natural world. Every living ecosystem already operates on this principle. The energy that flows through a forest canopy captured by photosynthesis and cascaded through trophic levels derives entirely from the continuous solar flux, with the forest's structural complexity, its standing biomass, its soil carbon, its fungal networks representing not a stock being depleted, but a steady-state configuration maintained by the balance of inputs and outputs. A termite colony of the African savanna builds mounds that regulate internal temperature to within 1 degree Celsius of a stable set point across the full range of ambient temperature variation using a system of passive airflow channels, whose geometry has been refined over tens of millions of years of evolutionary pressure, achieving what a human engineer would require powered mechanical systems to replicate using no external energy input, beyond the metabolic heat of the colony itself. This is not offered as evidence of prior intelligence in termites. It is offered as evidence that the principle of flow-based integration-oriented design is not exotic. It is the operating mode of every successful long-duration biological system on this planet. A civilization that understood this and redesigned itself accordingly would not be doing something unprecedented. It would be converging on the same solution that evolution has found repeatedly at every scale of biological organization. Materials tell a parallel story. The durability that human civilization prizes in its construction concrete steel engineered polymers is precisely what makes its residue persistent in the geological record and disruptive in living systems. Materials designed to resist natural decomposition accumulate in environments where decomposition is the mechanism by which nutrients cycle back into productive use. A civilization oriented toward integration would favor materials that perform their function and then return to biogeochemical cycles without disruption, materials that behave in their end-of-life chemistry more like organisms than like monuments. The archaeological record of such a civilization would be by design nearly empty. Its most advanced artifacts would leave no more trace than a fallen tree, which is to say they would leave chemistry not shape, and the chemistry would be indistinguishable from the background chemistry of biological decomposition. The absence of durable artifacts would not indicate a civilization that lacked sophistication. It would indicate a civilization that had reached the specific form of sophistication that no longer requires durability as a measure of value. There is a concept in systems ecology called the climax community, the stable self-sustaining ecosystem configuration that a given region moves toward over successional time, given sufficient stability in climate and soil conditions. A climax forest is not static. It experiences disturbance, gap formation, and regeneration constantly. but it maintains a characteristic species composition, a characteristic energy throughput, and a characteristic relationship between production and decomposition that is remarkably stable across centuries. Ecologists have noted that climax communities tend to be characterized by high biodiversity, tight nutrient cycling with minimal external loss and complex webs of mutualistic dependency among species, exactly the properties that make them resilient to perturbation, while also making them from the outside nearly invisible as products of any directed process. They look like nature at equilibrium because that is what they are. A civilization that reorganized itself along ecological principles that treated its own social and technological architecture the way a mature forest treats its species composition as a system to be maintained in dynamic stability rather than expanded indefinitely, would be moving toward its own kind of climax configuration. And a climax configuration by definition does not announce itself. It simply persists. The beings capable of this transition would not have been wiser than us by nature or by disposition. They would have been wiser by necessity, filtered by the consequences of their own extractive phase in ways that either ended them or reshaped them into something more compatible with long-term planetary residence. That filtering is not gentle. Every civilization's extractive phase produces feedback ecological degradation resource, constraint climate instability, the narrowing of options that follows from the systematic consumption of the conditions that made complexity possible in the first place. The civilizations that survive that feedback are the ones that read it accurately and respond before the options close entirely. Whether any civilization has ever done that successfully on this planet or elsewhere is a question the geological record cannot answer with confidence. What it can do is preserve in its chemistry and its biology and its atmospheric composition the outcome a planet that still works, still supports complexity, still maintains the narrow conditions under which minds can form and ask questions about what came before them. What those minds find when they look carefully at the world they have inherited is not a ruin. It is a functioning system whose history is longer and more layered than any single framework has yet been adequate to describe. The Unread Archive. In 1977, researchers aboard the research vessel Nor deployed a deep-towed camera sled along the Galapagos Rift, a section of the mid-ocean ridge system running along the floor of the eastern Pacific at a depth of approximately 2,500 meters. What the camera returned was unexpected enough to require confirmation: hydrothermal. Previously theoretical venting superheated mineral-rich water into the near-freezing abyssal dark surrounded by communities of organisms, tube worms, clams, crabs and bacterial mats living entirely without sunlight, sustained by chemosynthesis rather than photosynthesis, deriving energy from the chemical reactions between vent fluids and seawater rather than from the solar flux that drives every ecosystem familiar to biology at that time. The discovery was significant not merely as a biological curiosity, but as a conceptual recalibration. It demonstrated that the conditions required for complex life were less constrained than the existing framework assumed, and that entire ecosystems could persist in environments so unlike the surface that they would have been dismissed before the evidence as incompatible with biology. The deep ocean, it turned out, was not an empty archive. It was an archive that had simply not been opened. The deep ocean floor covers approximately 335 million square kilometers, roughly 71% of Earth's total surface area. Of that area, less than 25% has been mapped at a resolution comparable to the topographic maps available for the surface of Mars, which has been surveyed by orbital instruments for decades at horizontal resolutions of roughly 100 meters per pixel. The floor of Earth's oceans, by contrast, is known in most regions at resolutions of 5 kilometers or coarser, sufficient to identify the gross features of mid-ocean ridges, abyssal plains and deep-sea trenches, but entirely insufficient to detect features at the scale of human-built structures, geological anomalies smaller than a mountain range, or sediment deposits with unusual chemical properties distributed across areas smaller than a large city. This is not a complaint about the state of oceanographic technology. It's a statement about the size of the gap between what is known and what could in principle be known about the largest continuous environment on the planet's surface, an environment that, because of the weight of the overlying water column and the darkness and pressure of the deep, has been effectively inaccessible to systematic observation until the development of remotely operated vehicles and autonomous underwater survey systems within the last few decades. The deep ocean sediment record is in certain respects a more faithful archive of Earth's chemical history than the continental geological record. On land, sedimentary sequences are interrupted by erosion, deformed by tectonic compression, and disrupted by the intrusion of igneous material in ways that create gaps and discontinuities in the record. On the deep ocean floor, sediment accumulates continuously in the near stillness of the abyssal environment layer by layer, at rates of a few millimeters to a few centimeters per 1,000 years, preserving a chemical record that in some regions extends back tens of millions of years with relatively little physical disruption. The foraminifera, single-celled organisms whose calcium carbonate shells rain continuously to the ocean floor when they die, preserve within their shells isotopic records of ocean temperature and chemistry at the time of their formation, and their shells accumulate in the sediment in sufficient density to provide a nearly continuous record of surface ocean conditions across geological time. This is the archive that paleoceanographers use to reconstruct ancient climate states, and it is at its best extraordinarily detailed. But it is also an archive that has been sampled at only a tiny fraction of its total area, through a relatively small number of deep-sea drilling cores concentrated in regions accessible to research vessels and prioritized for their relevance to known scientific questions. The question of what that archive might contain in its unsampled regions is not one that current science is equipped to answer, and the intellectual honesty required by that situation is more demanding than it might initially appear. It is not merely that the ocean floor has not been fully explored, it is that the frameworks used to plan exploration are themselves shaped by prior assumptions about what is likely to be found, and prior assumptions, by definition, are less reliable guides in the specific places where the most unexpected things are most likely to have been preserved. The hydrothermal vent ecosystems discovered in 1977 were not found through a targeted search for chemosynthetic life in the deep ocean, because chemosynthetic ecosystems were not considered a realistic possibility before they were found. They were found because researchers were mapping the mid-ocean ridge system for geological reasons, and the camera happened to be looking at the right place at the right time. The history of oceanographic discovery is full of this structure. The most significant findings have consistently come from the intersection of systematic survey and genuine openness to the unexpected, rather than from the targeted search for phenomena already anticipated by existing theory. What makes the deep ocean relevant to tonight's question is not a specific anomaly discovered. There, no such anomaly relevant to a prior civilization has been formally identified in the deep sea record. What makes it relevant is its character as an archive, vast, chemically faithful over long timescales, extraordinarily undersampled and governed by preservation conditions different enough from the continental geological record that the two archives complement each other in ways that the scientific community is only beginning to systematically exploit. If a prior civilization left chemical traces in the planetary system in isotopic ratios and trace element distributions in the specific history of ocean chemistry across the relevant periods, then the deep ocean sediment record is among the places where those traces, if they exist, would be most likely to have survived in recoverable form. Not because anyone has looked there for them, because no one has looked there for much of anything yet at the resolution that would be required to find something this subtle across an area this large. The archive is not empty. It is unread, which is a different condition entirely, and the difference between those two states is where the fifth trace quietly waits. The archive that spoke. Every known human culture has a story about the world before this one. Not a story about the world's creation from nothing, though those exist too, but specifically a story about a prior world, a previous configuration of existence that ended and was replaced by the present order. The Hopi people of the American Southwest preserve an account of 3 previous worlds, each ending in catastrophe, and each succeeded by a new emergence through which surviving beings carried forward the knowledge of what had been lost. The ancient Aztec cosmology describes 4 previous suns, 4 complete ages of the world, each with its own dominant beings, each ending in a different form of destruction. Before the 5th sun, the current one was set in motion through ritual sacrifice at Teotihuacan. The Hindu tradition articulates a system of yugas, vast cycles of cosmic time in which the current age, the Kali Yuga, is the last and most degraded of 4 successive epochs preceded by ages of progressively greater knowledge and moral clarity. Norse cosmology places the current world in a framework that assumes prior creation, the giant Ymir, whose body became the material of the existing cosmos, implies a world before the world, an order that had to be dismantled before the present one could take shape. These traditions are geographically dispersed, linguistically underway, and historically independent. What they share is structural, the insistence that the world as currently experienced is not the first version of itself, and that what came before, though gone, left consequences still operating in the present. The conventional interpretation of this convergence is straightforward and not unreasonable. Human cultures confronting the evidence of geological catastrophe preserved in oral tradition, floods, volcanic eruptions, periods of prolonged darkness or cold following major impact events, constructed cosmological frameworks that place those catastrophes within a narrative of world ages, giving structure and meaning to discontinuity. The flood traditions that appear across cultures from Mesopotamia to Mesoamerica to South Asia have been linked in various scholarly analyses to the genuine geological and climatic disruptions of the late Pleistocene and early Holocene. The flooding of the Black Sea basin, the inundation of vast coastal areas following glacial melt the Younger, Dryas cold interval that disrupted human populations across the Northern Hemisphere around 12,000 to 800 years ago. These were real events experienced by real people whose descendants preserved the memory in the only medium available to pre-literate culture's story. The World Age framework is, on this reading, a cultural technology for encoding historical discontinuity in memorable, transmissible form. That interpretation is plausible. It accounts for much of what the mythological record contains. What it accounts for less comfortably is the specific character of the prior world in these traditions, not merely that it ended, but that it was different in kind from the present one, populated by beings with capabilities or qualities that the current world lacks, and that its ending was not simply a catastrophe but a transition, a passage from one mode of existence to another. The Hopi emergence narratives describe the beings of previous worlds not as primitive ancestors, but as entities with spiritual knowledge and relational capacities that degraded across successive world ages, each emergence representing not progress, but a fall from a higher integration into a lower one. The Aztec sun years are similarly structured. Each previous sun was associated with a different dominant element and a different type of being, and the transitions between them were not improvements but replacements. One configuration superseded by another through destruction, not development. The Hindu Yugas follow the same directionality in reverse, the Satya Yuga. The first and longest age was characterized by complete knowledge and righteousness. The Kali Yuga, the present one, is characterized by ignorance, fragmentation, and the degradation of understanding. The arrow of these traditions points consistently backward toward a higher prior state, not forward toward an improved one. This directionality is unusual in a specific way. Cultures that construct cosmological narratives from the raw material of lived experience tend to project their own developmental arc, the learning, the accumulation of skill, the improvement of technique onto their understanding of history. Progress narratives in some form appear across many cultural traditions because progress is the local experience of any community that learns from its mistakes within a human lifetime. The World Age traditions, by contrast, invert this expectation systematically. They describe not progress from simple origins to complex present, but degeneration from complex origins to diminished present. The consistency of that inversion across independent traditions, each arriving at the same structural claim through different narrative forms, different cosmological vocabularies, different specific content, is the detail that sits in the back of careful thinking without fully dissolving into the conventional explanation. There is a lake in the highlands of Bolivia, Lake Titicaca, sitting at an elevation of 3,812 meters above sea level, that carries in its own traditions and in its physical geography a particular kind of layered significance for this question. The ruins of Tiwanaku, one of the most sophisticated pre-Columbian civilizations of the Andes, lie on its southern shore, and the Aymara traditions associated with that site speak of a prior people, the Cholpats, who inhabited the world before the current sun rose, living under a different light building in ways that the current people could not replicate, and being destroyed when the present solar order was established. Whether the Chilpa represent a cultural memory of an actual prior population, a mythological encoding of astronomical transition, or a narrative explanation for the presence of architectural achievements that later inhabitants found difficult to account for, is a question the archaeological record cannot currently resolve. What Tiwanaku itself preserves in the precision of its stonework and the sophistication of its hydraulic engineering is evidence that the gap between mythological claim and material capability is not always as wide as the conventional timeline assumes, which is not the same as saying the mythology is literal history, but is also not the same as saying it contains nothing recoverable through careful analysis. The mythological archive is the most contested of the traces followed tonight, and appropriately so. It is the one most susceptible to the pattern recognition problem identified in the skeptic chapter. The human tendency to find coherent narrative in data that may be structured only by the universal features of human cognition and the universal experience of geological catastrophe. That susceptibility is real. The convergence of world-age traditions across independent cultures is striking, but striking convergence is also what we would expect from minds shaped by the same cognitive architecture, encountering the same kinds of disruption across the same planet's geological history. The trace is real as a phenomenon. Its interpretation remains open. What all 5 traces share, held together quietly at this point in the evening, is a common structure. They are each patterns that fit naturally within existing explanatory frameworks, and yet retain at their edges a residue that those frameworks do not fully absorb. That residue is not proof. It is the shape of an open question, and the question it holds most persistently is not whether a prior civilization existed, but what kind of world it would have left behind if it had. What it means to inherit a world. On the Orkney Islands off the northern coast of Scotland, there is a stretch of agricultural land along the western shore of the mainland island, where the soil contains at depths between 30 and 60 centimetres below the current surface. A dark, dense layer of what archaeologists call plagan soil, deliberately built up over centuries by Norse and pre-Norse farmers who mixed their fields with composted turf seaweed, animal manure, and household ash to compensate for the thin, nutrient-poor soils of the subarctic Atlantic margin. Carbon dating of the organic material within these plagan horizons places their formation across a span of roughly 1,000 years between approximately 800 and 1800 CE. The farmers who built these soils did not think of themselves as building anything for posterity. They were responding to immediate agricultural necessity, improving the ground they worked each season in order to feed themselves and their families through the following winter. The consequence, a chemically distinct soil horizon persisting 8 centuries after the practice that created it, was not intended as a legacy. It was the incidental residue of sustained practical engagement with a specific piece of ground preserved because the conditions of cool, moist Atlantic climate slowed the composition that would otherwise have erased it. The current farmers working that land inherited a productivity they did not create, and may not fully understand the origin of. They are the beneficiaries of a decision made by people who never imagined them. This is what inheritance looks like at the scale of a millennium and a few dozen centimetres of soil depth. The principle does not change when scaled to geological time and planetary chemistry. It only becomes harder to see because the inherited conditions become so thoroughly integrated into what we call the natural baseline that the distinction between inherited and original dissolves entirely. Every breath drawn tonight contains oxygen, whose atmospheric concentration was established over billions of years of photosynthetic activity by organisms that had no awareness of what they were producing, no intention of maintaining an oxygen-rich atmosphere for the benefit of future complex life, and no existence beyond their own metabolic moment. The oxygen is inherited in a functional sense from billions of years of biological labour that preceded us, and that built the atmospheric conditions we take as given. We are already living inside an inheritance whose depth and complexity dwarfs anything a human cultural tradition could transmit. The question that tonight's traces introduce is simply whether that inheritance might have one additional layer, a layer contributed not by mindless biological process, but by something that understood at some level what it was doing. The concept of second occupancy of arriving on a planet that has been shaped by prior presence changes the ethical structure of the relationship between a civilization and its environment in ways that are worth examining with some care. First occupancy implies a kind of originary relationship with a place you found it, you shaped it. You bear the particular responsibility that comes from being the first agent to impose an intentional structure on a system that had none before. Second occupancy implies something different, not originary relationship, but inherited one with all the obligations and humilities that inheritance entails. You did not make the conditions that sustain you. You received them from processes and possibly from presences that preceded you in ways you cannot fully reconstruct. That reception carries its own kind of responsibility, not the responsibility of a creator toward a creation, but the responsibility of a steward towards something whose history is longer and more complex than the steward can fully know. This distinction matters practically, not only philosophically. Civilizations that operate from a first occupancy framework, that treat their planetary environment as a resource system to be developed and exploited by the first intelligence capable of doing so, make a specific set of decisions about the rate at which resources can be consumed, the degree to which natural systems can be disrupted before recovery becomes improbable, and the relationship between short-term productivity and long-term habitability. Those decisions are calibrated to a world conceived as raw material unfinished, waiting to be shaped by the first mind capable of shaping it. A second occupancy framework produces different calibrations. It suggests that the planetary system arrived in its current condition through a history longer than the current occupants can reconstruct, that the stability and productivity of that system may reflect prior interventions and adjustments now invisible in the record, and that the appropriate relationship to that system is one of careful engagement rather than confident exploitation. Not because prior occupants designed the system for their successors, there is no evidence for that claim and no reason to assume it, but because the depth of the history implies the depth of the interdependencies, and the depth of the interdependencies implies the fragility of the conditions that currently make complex life possible. There is a term in ecology, shifting baseline syndrome, that describes a specific cognitive error made by scientists, managers, and ordinary people when assessing the health of an ecosystem across time. The syndrome involves the unconscious recalibration of what counts as normal for an ecosystem as conditions degrade, so that each generation of observers treats the depleted conditions they first encountered as the natural baseline against which subsequent change is measured, rather than comparing present conditions to the undepleted state that preceded human impact. Fisheries biologists identified the syndrome formally in the 1990s, noting that stock assessments consistently underestimated historical fish abundance because the scientists conducting the assessments had no personal experience of the pre-industrial ocean, and therefore treated the already depleted mid-20th century ocean as their reference point for normality. The syndrome operates wherever human memory is shorter than the timescale of the change being assessed, which is to say almost everywhere that human impact on natural systems has been ongoing for more than a generation or two. The geological version of shifting baseline syndrome is more severe and more difficult to correct than the ecological one, because the timescale of the change is not decades but millions of years, and because there is no instrumental record, no oral tradition, and no ecological memory that bridges the gap between the prior state and the present one. If a prior civilization altered planetary conditions in ways that have since been integrated into what we call the natural baseline, we have no reference point from which to detect the shift, because every instrument we use to define normalcy is itself calibrated to the post-shift conditions. We cannot see the alteration because we are inside it, measuring everything else against it as though it were the original. This is not a failure of science. It is a structural property of the epistemic situation of any civilization that arrives, after enough time has passed, to erase the evidence of the prior state. It means that the question of whether we have inherited a world shaped by prior intelligence is not answerable by comparing present conditions to an unaltered baseline, because the unaltered baseline, if it ever existed, is no longer accessible in any recoverable form. What remains accessible is the present, the world as it currently exists, functioning at a level of complexity and habitability that is by any reasonable measure remarkable for a planet of this age size and position. Whether that remarkability is entirely the product of natural process, partially the product of prior intelligent intervention, or some combination of both in proportions that cannot now be determined, these are questions whose answers lie, if anywhere, in the Layers of evidence still unexamined in the archives, still unread, and in the frameworks not yet developed enough to ask the right questions of the data already available. The traces followed tonight do not resolve this question. They do something more modest and, in some ways, more valuable. They preserve its shape, hold its outline steady against the pressure to close it prematurely and return it intact and unresolved to the dark and the quiet where it belongs. What that question does to the experience of lying on a planet in the dark, the specific weight of the ground beneath you when you allow its history to be longer and more layered than you can fully account for, is the territory that the final 2 chapters move through, slowly toward rest. The weight of an open question. Intelligence, as far as the current scientific record indicates, has one confirmed address in the universe. This planet, this thin shell of temperate atmosphere, this specific arrangement of water and carbon and mineral that has, against the long odds of cosmic indifference, maintained the conditions for complex thought across at least the last several 100,000 years. That singularity, the fact that we know of no other minds, no other civilizations, no other places where the universe has folded back on itself in the specific way required to produce a creature, asking questions about its own origin, gives the question followed tonight a particular kind of weight that is easy to mistake for loneliness, but is more precisely described as responsibility. If we are the only intelligence currently operating in this region of the galaxy, then we are also the only intelligence currently capable of asking what came before us on this planet, of examining the geological and biological and atmospheric records with enough sophistication to notice the traces that might or might not be there, and of holding the question open long enough to allow better instruments and better frameworks to approach it more honestly than current ones can. The loneliness of that position is real. So is the obligation it creates. There is a quality of attention that open questions demand which closed ones do not. A closed question, one that has been answered, filed, and incorporated into the working framework of a discipline, requires only the capacity to remember and apply its answer. An open question requires something more active and more uncomfortable, the sustained willingness to sit with uncertainty without resolving it prematurely, to hold competing explanations in parallel, without collapsing them into a single preferred narrative, and to remain genuinely curious about the residue that the preferred narrative leaves unexplained. This is harder than it sounds, and not only because uncertainty is psychologically uncomfortable, it's harder because the institutional structures of scientific inquiry, for entirely understandable reasons, reward resolution over openness. Papers that answer questions get published and cited more readily than papers that carefully articulate why a question cannot yet be answered with the available data. The consequence is a systematic pressure toward premature closure that operates not through bad faith, but through the ordinary incentive structures of professional knowledge production. Open questions about prior civilizations on Earth exist at the extreme end of this pressure because the cost of appearing to take them seriously in terms of professional credibility association with non-rigorous traditions of inquiry and the risk of being misread as endorsing claims far beyond what the evidence supports is high enough to discourage all but the most carefully positioned researchers from engaging with them in print. What that pressure produces in the specific case of the question followed tonight is not suppression, but ziyasha, a different and in some ways more durable condition. Suppressed questions leave traces of their suppression. Controversies, dismissals, the record of arguments made and rejected. Silent questions leave nothing. They simply do not appear in the literature with the frequency their structural importance might warrant, and their absence from the literature is then cited circularly as evidence that the scientific community has examined and dismissed them, when in fact the community has largely declined to examine them at all, for reasons having more to do with professional risk than with the quality of the underlying question. The Silurian hypothesis paper published in 2018 is notable precisely because it represents one of the rare occasions when researchers with mainstream credentials chose to engage with the question in rigorous form, defining what evidence would look like, modelling what would and would not survive in the geological records, and arriving at conclusions careful enough to avoid the twin failures of premature confirmation and premature dismissal. The paper did not generate a research program. It generated citations in popular science writing and a small number of follow-up commentaries, and then the literature moved on. The question remains open not because it was answered, but because the incentive to pursue it remains low relative to the professional risk of being associated with it. This matters for tonight's question in a practical sense, because it means that the absence of active scientific investigation is not equivalent to the absence of scientific possibility. The space of questions that could in principle be investigated with existing or near-future methods is vastly larger than the space of questions that are currently being investigated. And the selection of questions for active inquiry is shaped by factors: funding availability, disciplinary norms, professional risk, the legacy of prior research programs that have no particular relationship to the importance or tractability of the questions themselves. Some of the most significant questions about Earth's history are receiving intense investigation because they connect to contemporary concerns, climate sensitivity, biodiversity dynamics, the carbon cycle. Others, equally significant in principle, receive little attention because they do not connect to those concerns in obvious ways, and because the communities of researchers best positioned to investigate them have not, for structural reasons, oriented their work in that direction. The question of prior terrestrial intelligence is at this moment largely in the second category. That categorization is not permanent. It reflects current conditions, not the intrinsic limits of the question. What changes when a question moves from the second category to the first is not the question itself, but the instruments brought to bear on it, the specificity of what is searched for, the resolution of the archives, examine the sophistication of the models used to distinguish signal from noise. The deep ocean sediment record examined in the previous chapter has not been searched for isotopic signatures of prior industrial activity, because no one has defined what those signatures would look like at the relevant timescales with sufficient precision to make the search tractable. The biological record has not been systematically examined for patterns of ecosystem engineering inconsistent with purely natural evolutionary dynamics, because the framework for distinguishing such patterns from natural variation has not been developed. These are not impossible investigations. They are investigations that require prior conceptual work, the definition of what would count as a positive result, the modelling of what the null hypothesis would look like, the development of analytical methods sensitive enough to detect the relevant signal above background noise, and that conceptual work has not been done because the question has not been taken seriously enough by enough researchers with sufficient resources to motivate it. The open question followed tonight is not smaller for being unresolved. It is in a specific way larger because the size of a genuine open question is measured not by how much is known about it, but by how much remains possible within it, and the space of what remains possible within this question is, by any honest assessment, still very large. The planet beneath you has been accumulating its history for 4.5 billion years through processes that no current framework fully describes across timescales, that no human institution has yet developed the patience to examine with adequate resolution. What that history contains, all of it, including the parts that have left no recoverable trace, is something that no living mind can fully know. The appropriate response to that condition is not certainty in either direction. It is the particular kind of alertness that comes from knowing you are standing at the edge of something whose depth you cannot see. That alertness held quietly in the dark is the last trace worth following before the question dissolves into rest. The ground beneath you is already old. At a certain depth of tiredness, questions stop demanding answers and become something closer to companions' presences that accompany you into sleep without requiring resolution before you arrive there. The question followed tonight has that quality if you allow it to. It does not insist on a conclusion. It does not harden into a claim that must be accepted or rejected before the mind can rest. It sits instead at the edge of what is knowable, neither confirmed nor dissolved, holding its shape in the way that genuine open questions hold their shape, not by force of argument, but by the simple persistence of the gap between what the evidence shows and what the evidence fully explains. That gap is not a failure. It is the honest condition of inquiry at the boundary of deep time, where the instruments grow less precise and the questions grow larger, and the appropriate response is something quieter than certainty. The planet beneath you tonight is 4.5 billion years old. That number is available to the intellect, but it's not available to the body in any direct sense. The body knows weight, temperature, the slight give of the surface it rests against, the rhythm of breath moving through it. What the body knows tonight is a surface that is solid and old and continuous with something much larger than the room you're in, something that extends downward through layers of sediment and bedrock and mantle and core in a succession of conditions so different from the surface that they constitute in a meaningful sense different worlds stacked beneath you. You are resting on the topmost layer of an archive whose deeper sections are written in languages, pressure, temperature, mineral phase transition, that no human instrument has yet fully learned to read. The archive is not hostile to reading. It is simply deep, and depth requires patience that the history of human inquiry is only beginning to develop. Somewhere in that archive, in a sediment layer, in a chemical ratio, in the specific distribution of a trace element across a formation of ancient rock, there may be a signal, not a message, not a warning, not a monument to anything, just a number that sits slightly outside the range that purely natural models predict in a layer, from a period when the geological record is already sparse and the interpretation already uncertain. That number, if it exists, is not waiting to be found in any dramatic sense. It is simply there or not there, embedded in the chemistry of a planet that has been processing its own history for longer than complex life has existed. Whether anyone finds it, whether the right instrument is ever pointed at the right layer with sufficient resolution to distinguish signal from noise, whether the framework required to interpret such a signal is ever developed, these are questions that belong to the future, to research. Not yet born, working with methods not yet imagined, asking questions whose precise form has not yet been articulated. Tonight, they do not need to be answered. They only need to be acknowledged as open and then set down. The biological systems around you, the microbes in the soil, the mycorrhizal networks threading through root systems, the bacterial communities in the air you're breathing are all carrying forward in their structure and their chemistry and their evolutionary history. The residue of every prior configuration of life that preceded them on this planet. They are archives in their own right, written in the molecular language of gene sequences and metabolic pathways, and they are almost entirely unread in the sense that matters for tonight's question. What they remember in the deep structural sense of biological memory extends back further than any human tradition, further than any written record, further than any artifact. They remember in some functional sense a planet that was different, colder, warmer, more or less oxygenated, inhabited by organisms whose forms have no living analogues, and they carry that memory forward into the present without any awareness of what they carry. You are breathing that memory tonight. It moves through you with each breath indifferent to its own depth. The open question followed tonight does not resolve. It was not designed to resolve. It was designed to be held lightly without urgency, in the specific way that the most honest questions about the deepest things can be held by a mind willing to let the absence of an answer be for now enough. Whether a civilization preceded us on this planet, whether it left traces too subtle for current instruments to distinguish from background variation, whether the world we have inherited carries within its chemistry and its biology and its atmospheric composition the residue of prior intelligence, these questions remain exactly where they were at the beginning of this evening, open, structurally sound, epistemically humble and patient in a way that deep time has always been more patient than the minds it occasionally produces. The ground beneath you is already old. Whatever its full history holds, it continues forward without pause, absorbing, recycling, maintaining the narrow conditions under which something like you can exist and wonder about what came before. Your presence on this surface is one brief interval in that continuity. The question you have carried through this evening is another. Both are real, both are temporary, and both for now can rest. Rest now, traveller. A zircon crystal recovered from the Jack Hills of Western Australia measures roughly the width of a human hair. It is 4.4 billion years old. Under the right instrument, it still carries temperature data from oceans that no longer exist. Not as a message, not as perhaps as a record kept intentionally for anyone who might later think to ask, but simply as the residue of conditions that prevailed when the mineral lattice formed and then locked and then held through everything that followed. Through the formation of continents and their dispersal, through the rise and fall of oxygen, through mass extinctions and the slow recovery of biospheres on the other side of them, through whatever happened and whatever did not happen in the intervals between those events that the record does not fully describe. The crystal did not survive because it was important. It survived because its chemistry happened to be stable enough and its burial circumstances happened to be right, and the researchers who recovered it happened to be looking in the right place for reasons that had nothing to do with it specifically. It is the thinnest thread of evidence from the deepest available time, and it carries real data, and it is not enough for him to answer the question we have been following tonight. That is the honest condition of the question, and it does not need to be otherwise in order for the evening to have been worthwhile. There is a particular kind of rest that comes not from having understood something fully, but from having held it carefully, from having turned a question over in the hands of attention long enough to feel its actual shape rather than the shape you assumed it had before you began. The question of what preceded us on this planet, whether anything did what traces it might have left, and whether we would know them. If we found them, this question has a shape that resists the pressure of a clean ending. It was not going to resolve tonight. The geological record was not going to yield a definitive answer between the moment you pressed play and the moment sleep arrives. What it offered instead was the texture of genuine uncertainty held without the anxiety that uncertainty often carries when it is resisted, rather than received. The planet you are resting on has been here through all of it, through the carbon excursions and the atmospheric oscillations and the biological experiments that did not persist and the ones that did. It has processed each of these events with the same indifference it will eventually apply to everything that is happening now, filing it into the sediment, incorporating it into the chemistry, smoothing the evidence into something that will look from a sufficient distance of time like the ordinary behavior of a world that has always been exactly this way. That smoothing is not a loss to mourn. It is simply what deep time does to the particular. And it applies to everything, to catastrophes, to civilizations, to the contents of this evening's quiet attention, and eventually to the question itself. Not because the question will be answered, but because the minds that hold it are like everything else temporary. The question will outlast any individual holding of it. The planet will outlast the question. There is something faintly settling in that if you allow it to be, not consoling in any simple sense, but settling the way that recognizing the scale of something very large can release the pressure of needing to resolve it personally tonight before sleep. Perhaps the detail that refuses to go away is the smallest one that the crystal exists, that it carries a number, that the number is real, and the oceans it remembers are gone, and that this situation, a fragment of deep time preserved by accident, read by instruments built by minds that appeared billions of years after the event being recorded, is not exceptional. It is the ordinary relationship between any intelligence and the planet it finds itself on. You are reading the archive you were born inside with instruments made of the same material as the archive itself, looking for traces of a presence you cannot confirm and cannot rule out on a night that will pass into the sediment of your own memory and eventually dissolve there into something you will not be able to fully reconstruct from the fragments that remain. That is enough. The question is held. The archive is deep. The crystal is 4.4 billion years old and the width of a human hair, and it remembers water. Let the ground hold you now, traveller. Let the layers go down beneath you as far as they go through the soil, through the bedrock, through the chemistry of things that happened before memory was possible. And let all of it be for this night simply the depth of the place you are resting in, without demand, without resolution, without the need for the question to be anything other than open and patient and very, very old. The record preserves the shape of the question without resolving what it meant. Sleep well.